Okay, I think we can get started now. So thanks everyone for joining us in the breakout session. Today we have Dr. Soeren Brandt speaking to us. So Dr. Brandt received his PhD in applied physics from Harvard University in machine learning and materials chemistry for bio-inspired sensors. Since graduating, Soeren is developing quantum mechanics and machine learning solutions for AI-driven drug discovery at 1910 Genetics. Okay, so I'll hand it over to you, Dr. Brandt.
Thank you very much. I think my audio cut out for a briefest of moments, but it's great to be here. And thanks so much for having me. Over my PhD, I work with a number of co-op students from Waterloo. So you'll be seeing a lot of research that has been done in collaboration with those students. And I'll be happy to share any insights from those experiences. So what I want to talk today, and in the context of the environment session, are challenges that we looked at in this research related to the transportation of hazardous materials. And so one of the things that comes immediately to mind are crude oil spills, which are a common occurrence in the US and across the globe. In the US and North America alone, 3 million gallons of crude oil are spilled every year. This is a single example that was particularly bad in Alaska in 2006, but these kinds of events are fairly frequent with over 9,000 crude oil spills every year. And much of those challenges are related to corrosion and the corrosivity of crude oils. And the key challenge here is that crude oil in particular has a high variability in its hazardousness. So it ranges from the very, very corrosive to the somewhat more manageable kinds of crude oils, and understanding which crude oils are challenging to transport and which ones aren't is a key challenge. And the cleanup, as I'm sure most of you are aware, can be a major challenge in and of itself. And if we look to nanomaterials, I'm sure I don't have to tell this audience about the lotus leaf, which is one of the most common examples of self-cleaning materials that exhibits a hydrophobic oil layer that covers a nanostructured surface of the leaf, which leads to superhydrophobicity and makes the surface of the lotus leaf super repellent. And the feature here is that any dirt that covers that leaf could just be run off during the next rain. Now, I'm not proposing that we use these kind of materials to cover every area around crude oil spills to have oil just run off, but you can use these kinds of nanomaterials to add functionality to other types of surfaces. For example, anti-fogging or anti-freezing applications. You can use it to enhance the condensation of water, and you can control the level of imbibition into a porous substrate by fine-tuning the nanoporous structures on the surface of these kind of materials. Now, these are all examples that friends and colleagues of mine have worked at over the years relating to our work in the Eisenberg lab. And they involve a kind of material that is used in nature for structural color. So what you're seeing here is a very prominent example of a morpho butterfly that shows vibrant blue color due to Christmas tree-like structures on the surface of its wings. And these structures refract light in such a way that blue wavelengths are reflected while yellow and red wavelengths pass through. And what you can see is when these structures are exposed to water, the water is repelled, but when you wet it with something like ethanol, the liquid infiltrates into the structure and you can see a color change. And so now you have a nanostructured surface material that exhibits two functionalities. One is a color change in response to infiltration, and the other is control over the imbibition and infiltration of those liquids. And so you can use that in an artificial material called inverse opals, where we assemble nanocolloids or nano-sized colloids of a few hundred nanometers into a close-packed array, and then infiltrate the structure with a matrix material like glass or some metal composite, typically oxides, and remove the structure to get an interconnected porous network that exhibits structural colors similar to the morphobutterfly. And the internal structure of the necks connecting these pores is such that you get a geometric threshold for infiltration that leads to infiltration in the case that the contact angle is very low and you have a highly wetting substrate like we saw with ethanol and the morphobutterfly wing, or you get, you prevent infiltration by preventing liquids that are non-wetting to infiltrate into the structure. And one of the things that we did during my time in the Eisenberg lab is we built a sensor with gradually increasing hydrophobic coatings to be able to identify different concentrations of, for example, ethanol in a mixture of water and ethanol. And this is particularly challenging because, as I'm sure many of you know, when you add a little bit of ethanol to water, the surface tension of water, which is very high, can change quite rapidly. And so this gives you a simple tool that works kind of like a pH sensor. For those of you who have used that, you just dip a little strip of some chemicals into a mixture, and then you compare the color change of these chemically modified areas to identify the pH of certain compounds. And you could build this for many different applications as friends and colleagues have done in the past. But what you're really aiming for ultimately to identify different crude oils is a sense that is more powerful. And the powerful kind of sense that we came to think of is smell. And think about the kinds of things that you can actually detect by sensing them. There's the nice, like flowers. There's the less nice, like rotting meats, a skunk, and other animals that use defensive thiols, for example. And then there's the outright hazardous, like nitrous oxides. There are certain biomarkers and crude oil, for example. And the way human noses, and by extension, other animals' noses do this is by using an array of olfactory receptors. And these kinds of receptors are typically biomolecules that respond to certain certain odors in a key lock principle. And humans have about 400 olfactory receptor genes and on the order of 50 million receptors, and dogs have significantly more owing to their much more prominent noses. Now, researchers have tried to mimic these kind of systems by building what are called sensor arrays. And so you typically use a number of differently functionalized nanomaterials that respond differently to different compounds. This is an example from MIT, where they use carbon nanotubes that are functionalized with so-called selectors, which are different chemical functionalizations to respond differently to different compounds. And then they're measuring the conductance through those carbon nanotubes. And there are other examples. There are microcantilever arrays where you typically use colloids that are functionalized with different materials. There are semiconductors and paper-based kinds of artificial noses. But the fundamental challenge to all of these is that you see degradation of the materials at different rates, which leads to sensor drift and makes the signals that you're measuring difficult to interpret. And so they're really no good. And they're also limited to the number of sensors that you can combine at a particular time. And so what we were really looking for was a simpler, more straightforward tool that would still give us more powerful responses. And so what we ended up building is a tool that is very similar to those color changing materials, where we use a similar structure of a bilayer titanium silica composite of nanoparticles that exhibits purple color. And then as we inject the liquids into an enclosed chamber, the atmosphere inside that chamber changes over time, and we can record that shift by observing the color of the crystal change over time. And you can see the purple color at the beginning and the bluish tint, the turquoise, towards the end. And so we can record this change over time, and this is an example given for hexane, and you can repeat this and use these profiles to record different kinds of compounds. And I challenge you to identify which of these is, again, hexane and which one isn't yourself. And so if we look at just the color change of these kinds of materials, we see that for many different compounds, like different alkanes and liquids like ethanol and water, we see that there's really a lot of similarity in the overall shift that we see over time. So it's really challenging to tell apart by looking at the before and after to identify which kinds of compounds are which. And you can actually train machine learning to identify different compounds, and you can see that you're all over the board. So you're doing better than chance by identifying the overall colored shift, but you're not outperforming a lot of other techniques that might be interesting. What instead we did is we looked at the shift over time. And so what you're seeing here is the movement of the peak of that color spectrum over time, typically over 10 minutes, and you can see that the diversity in terms of the signal that you measure is much stronger, and you're much more able to identify different compounds and actually mixtures as well, using the dynamics rather than the total shift. And so that can be further enhanced, which is something that we did in a follow-up study where we looked at the behaviors that you can see in different animals that are searching or not so much searching for certain odors. So these are hunting dogs. And when they're looking for ground animals, they're sniffing towards the ground in a very fast pace pattern compared to when they're looking for animals that are in the sky, like birds. They're using a long inhale method to look for those animals. And so the idea here is that you could use the same kind of sensor that mimics smell and uses sniffing patterns for different applications, like to identify different crude oils, to identify food spoilage, to find explosives, anything you can imagine a dog could potentially smell. And so we did that and showed that you can use different kinds of sniffing patterns to resolve features in those dynamic color shift spectra that we saw before, and improve the accuracy of the kinds of predictions you can make using machine learning. And so what I want to leave you with today, and in this very brief session, is that you can use nanostructures to combine different kinds of wetting and photonic effects in new and interesting ways to mimic the kinds of bio-inspired processes to sense very complex processes. And one way to do that is to use the dynamic processes that you see in evaporation, diffusion, adsorption, to mimic very complex senses in biological systems using much simpler tools. And in that effort, machine learning can be a very powerful tool to do that signal processing to avoid having a de novo understanding or theory of the kinds of signals that you would expect. And with that, I've hit my 15 minutes and I would love to answer any of your questions. Thank you very much. Oh, I actually can't hear you. Let me see. I'm sorry about that.
Hello? Sorry, can you hear me now? Okay, so if anyone has questions, either put it in the chat, or if you like, you can also turn on video and audio to share, but just keep in mind that there's a limit to 5 people sharing their video at the same time. So once you're finished your question, you can turn off your video to allow the next person to ask their question.
I can hear you now too, so this is
I think better. I was muted before.
There's something reloaded on my end too, so I'm as guilty as everybody else.
So we have a question from Eliana. She's asking, what ML methods do you use?
So we explored a couple of questions, and that's a very good and important question to ask when working with machine learning tools, because there's a lot out there. At the time, we decided to use mostly support vector machines for 2 reasons. For one, it's a very straightforward and simple tool that you can look a little bit under the hood. So support vector machines, if you're not using anything like a Gaussian kernel, it allows you to almost do the math by hand. So you can see which part of the signal gives you what output, and like which segments actually matter to determine what kind of compound or result or prediction you're making. In addition, support vector machines are in most cases very applicable and give very good results in comparison to other approaches, typically classical approaches like decision trees or Bayes regressions. Those are all the kinds of tools that work for specific applications, but support vector machines are kind of like a brute force tool that works very generally. And it requires much less training data than, for example, deep learning techniques or neural networks would need. And so those were the key motivations. We did try some other methods. So we used simple regression, which had some difficulty with some of the higher dimensions and nonlinearities. And we also tried to use transfer learning on convolutional neural networks, which worked okay, but support vector machines generally work much better. If I had to do this project again, I would probably be looking at recurrent neural networks, which are the current thing that's so hot right now. So that would be something exciting to try.
Thank you. So our next question is from...
And so in terms of another question was relating to the fast and long sniffing. The idea there was to inject liquid at different rates. So the original sensor that we worked with was just a glass chamber where we would drop a liquid onto the bottom surface and it would evaporate and then move towards the sensor. That is a very passive process where you're just waiting for things to happen. And as I'm sure you saw, it takes about 10 minutes for the whole signal to work out. And you can play around with that a little bit, but that was really the time frame that we found worked best. To accelerate that, the idea was, what if we injected not a liquid, but the gas directly? And so that allows us to mimic these kinds of sniffing behaviors. So we had a smaller box with the same crystal, and we would use pressurized nitrogen to inject gases from liquid reservoirs. So we would take the equilibrium vapor from above a liquid reservoir and inject that into a glass aluminum chamber, and the rate at which we did that we refer to as fast or slow sniffing. And so the fast sniffing was we inject for a second with a half-second pause and then re-inject with half a second. And so what you would get is you would increase the concentration in little humps. In contrast, the long sniffing was a 5-second injection with a 2.5-second break, and then we would remove all of those gases. And so what the feature that you're getting in addition to being able to do faster measurements is that you're seeing a lot more of the dynamics of adsorption and desorption, because the concentration in the chamber is increasing and decreasing dynamically. Whereas in the original chamber, where you just inject the liquid, you're just filling the gas with whatever liquid vapor, and there's no turning back really. And so you can probe a lot more of the dynamics, and you can compare volatile compounds that evaporate faster or more slowly using different approaches. And so I'm going through the next question. That's a very interesting question. So the question is relating to applications in food and flavor development, and using AI to develop new smells and compounds that we would find irresistible, which I think is a very American perspective on let's make this food smell even better by adding artificially AI created stuff. But there are efforts in using AI to design new odors and combinations of flavors, some of which is spearheaded by Google. I have talked to some leaders in flavor development. I don't remember the company, but there are some efforts to use AI to combine different smells. I'm not too familiar with the AI approaches that are used in those, since the kind of processing that we used is more, we have a time-dependent signal and we used time series analysis to understand what particular odor we're getting. So we didn't do the reverse of kind of creating an odor profile. But in terms of creating things like chemicals, for example, drug design, which is something which I'm working on now, you have a very similar process where you express a chemical in a written format, like a sentence or a word. And a word you can very much treat the same way like you would do a time series signal. So you can pretend that, I actually prepared a slide for that. So you can write something like aspirin in what are called smile strings, which essentially work the same way like a sentence would in natural language processing. And then you can use things like recurrent neural networks. The most recent iteration of those is long short-term memory recurrent neural networks that allow you to predict new compounds that are similar or might have similar properties. And so I imagine you could do similar approaches with odor profiles, where you want a particular sequence of odors to hit at a particular frequency, and you need to decide how to encode what kind of flavor or smell you can use, right? So for example, here, obviously O is for oxygen, C is for carbon, and what each of these characters mean is encoded in the SMILES language. And so if you have a similar language for odor profiles, you could use things like recurrent neural networks. There are methods to create sentence structures from just a number of keywords. So you can have AI write, for example, a news article about something that's currently happening. You could use similar approaches where you say, I want to have a flavor profile that is sweet but flowery, and use that to have AI pick kind of a combination of different things. So there are approaches. I hope this somewhat answered your question. I'm personally not working in the field, so maybe I missed something. So another question is, how do you figure out whether there is a use case for machine learning working with a particular set of materials in science and nanotechnology? That's a very good question. And one of the key challenges in AI and machine learning is typically figuring out what tool to use, like what flavor of machine learning you want to use. And then much bigger, what do you do with your data to actually train your machine learning model? And so something that people worry about quite frequently is the amount of data that they have. That's actually not the primary concern. You can use different approaches with limited data, but it's the quality of data that is often much more important. So imagine if you have a bunch of garbage, if you put garbage into your machine learning model, you'll get garbage out. It's the same thing with a lot of other processes. But if you're completely new to machine learning, something I would recommend and encourage you to do is to take Andrew Ng's course. That's Andrew NG on Coursera on machine learning, which is a very good introduction into just some of the basic ideas behind machine learning. But to give a better and more like direct answer to your question, in general, you can use machine learning on any type of data. So you can use structured data where you have, let's say, the size of a house, the number of bathrooms, the square footage, right? So that's very structured data that you have in a table, or unstructured data where you have images or audio signals, and there's methods to use for all of those. And there are many approaches that I've seen recently and over the last couple of years and decades, using machine learning to design new materials. The specific approach to use is in the details, but in general, I would say if you have data, there's going to be a machine learning tool to use for that. And it's more about figuring out how and what to use. So Bing asked, what about putting a GC column in between? I'm gonna answer that question. I'm not sure if I understand correctly, so please follow up if I miss some nuance. But what a GC column would do is it would spread out the different components in your odor profile, right? So GC would be gas chromatography. You could use HPLC on something like crude oil. And those are valid approaches to get a very high resolution answer to like what is actually in my mixture. So HPLC is something that you would do on drugs as you're processing them to determine purity. It's something that you can do on crude oils, although it's not commonly done. The challenge with GC and things like HPLC is that they're somewhat time consuming. So a GC MS study typically takes about 30 minutes to an hour. And it gives you a very granular understanding of what's inside of your mixture. And that's not always the question you want to answer, right? So for example, with crude oil, we're less interested in what's specifically in there, like what the composition is. Those are important questions, but they're not important when you're transporting them. What's important is how corrosive or explosive, how volatile, how fluid-like is the material. And so you're more interested in the properties. Think of it like this, right? Like you're meeting a new person and your choices between having a conversation with them or getting a list of all the chemicals that are inside of them, right? Like, sure, like knowing the chemical composition of the person will give you a lot of detail about them, but like it's not really what you're interested in meeting them, right? And so for the approach we chose here, we wanted to mimic the sense of smell in the sense that you're identifying different objects, like for example, a lemon or an orange, or something poisonous, something that has spoiled. You're not really measuring what's inside of your food at any given point, right? And so it was more about a qualitative understanding of what the compound is and predicting its properties rather than getting a detailed understanding of what is inside of the specific mixture. I hope that answered your question, but please feel free to follow up. Anuja asked, which were the major challenges applied with your research, especially when you incorporated machine learning? Thank you for that question. The biggest challenges for this specific project were figuring out what's repeatable and what actually works. So the choice of the color changing material was a little bit of a process. Originally, we started with the inverse opal-like structures, which we've been working with for at least a decade in the lab. But the challenge with those is that they're not super reproducible. Like they're qualitatively reproducible, but when you're looking at things with the spectrophotometer, you'll see minor differences. And so the film production of that color changing material took a little while to understand. In addition, it's really challenging to work with crude oils. So one of the key problems with crude oils is that there's the very volatile components like methane, ethane, and then there's very heavy components. So when you're working with a crude oil, it changes over time. So when we started the project, the focus was very much on identifying different crude oil compositions and properties. But that focus later shifted to a more research focus, like what can we actually identify and like what mixtures that we can make in the lab are interesting. And so I remember a time where we had like a giant metal rod filled with crude oil in the lab that had like different components that were very technical to get liquid out of to kind of prevent those light compounds from escaping. And then when you're working on a project that is that has a lot of nuance in terms of these dynamic processes, it is important to write down every single step that you take in great detail. So on this project, I believe at least 11 co-op students worked on, and 4 or 5 graduate level researchers, which means that as we were collecting on the order of 1,000 experiments, at some point it got lost in translation that you needed to place the box inside of a humidity chamber while you're assembling it. And so some some experiments were performed after assembling it outside, which led to water vapor getting into the chamber, changing the color of the crystal. And so the color change was less pronounced when we actually injected a liquid. And so those details are difficult to tease out when you have a very many step style process. So when you're embarking on a project like this, I definitely encourage you to really be meticulous about like writing down the details of all of the things. In terms of the machine learning, the machine learning part is the one that is fastest to iterate over, because when you're just working with a handful of experiments, you can very quickly iterate through different processes, and you're just running a bunch of Jupyter notebooks at the same time. That's really fun. What you need to be careful with is that you're somewhat principled about how to apply machine learning. And Ender Ng's course is very helpful in getting some idea of what that means. But in the briefest of sentences, it means having a clear structure about when to apply PCA, typically avoiding it if you can, and using just one machine learning tool at a time to really understand of what's going on. And then the same as with science in general, right? Like do several repetitions, right? Separate your data into a training and a testing set over and over again, and make sure that the testing set isn't at any point part of the training process. For example, using it to do the PCA first and then doing machine learning. That's important, not to keep those buckets separately and use testing only at the end. And then repeatedly identifying like what's the standard deviation of your accuracy, where do you see improvements, how do you tune hyperparameters. That's something worth looking at. Okay, I'm getting lost at which questions we already had, but I think Joshua is next. Could you elaborate on how you would go about changing your sensors when trying to detect the different types of compounds, identifying types of hydrocarbons versus spoiled foods? That's a very good question, and it's something that we've thought about quite a bit. The first thing that's easy to think about is whether or not you have a very volatile compound or you have a very non-volatile compound. So for example, the non-sniffing sensor that we had, where we would inject the liquid and it would evaporate, the time it takes for the vapors to diffuse depends on how volatile or non-volatile your compound is. And so that determined how long of a distance we decided to make the chamber. So we actually had the chamber that I showed is 8 centimeters tall. We tried less than that, 5 or 3 centimeters, and that will accelerate the time between you inject the liquid and when you're actually measuring or completing the whole signal. And so that is a very obvious lever to twist. Also, the porosity of the photonic structures matters in order to lead to condensation of liquids. So one phenomenon in adsorption is that when you have very small pores, you'll actually see more and faster adsorption of different liquids. And adsorption isotherms have a very unique profile depending on the compounds, and those can be influenced by the porosity. So if you're interested in a very specific kind of compound, it's worth looking at those isotherms to kind of design the size of your porosity around. The porosity we used was somewhat broad, and so we actually had a bilayer structure with different porosities. So we kind of had a general purpose type sensor, but for specific applications, you could be thinking about using more fine-tuned materials and sizes. For the specific example, right? So for example, hydrocarbons versus spoiled foods. Hydrocarbons come in the entire range of very volatile to not so very volatile. For the very volatile compounds, having a larger separation of the sensor and the injection side and a bigger a smaller porosity makes sense, because then you see both the absorption and you get that spread over time. And so your signal isn't over in the first 10% of your measuring time. If you're looking at spoiled foods, you're going to be looking at a more complex signal, and you're not going to be measuring all of the compounds that you see in the food. And so what I think is much more important in spoiled foods compared to hydrocarbons is the complexity of different compounds that you could have spoiling, right? So for example, spoiled milk is something very different from spoiled meat versus spoiled fruit. And getting that amount of training data and the diversity of the training set is going to be very much more important than in the hydrocarbons, where you can somewhat interpolate between different ones, right? Okay. Kelly is asking, it sounds like the sensor project you were working on was mainly qualitative. Do you think quantitative analysis could also be implemented? And if so, how? Thanks for asking that question. We actually did try to be a lot more qualitative, but because this was supposed to be just a brief 15-minute introduction, I cut a lot of that work. In terms of qualitative work, one thing that you immediately think about is if you have composition. So imagine you have two hydrocarbons or water ethanol mixtures, as were discussed in the beginning of the talk. Those are things that we did look at, and you can use support vector machines both for classification, so putting it into a bucket like this is hexane or pentane or something else. But you can also use it to predict mixing ratios by using regression algorithms. We actually do perform similarly well. So our squared values that we typically reach are above 0.9, 0.95 in that range, which is comparatively good for machine learning in many cases. And something that I was very passionate about is predicting physical properties. So what we tried is we used the same data we used for classification and predicted physical properties like the boiling point, the flash point of different compounds, the viscosity, which isn't really related to any of the processes. And we actually did quite well, both on compounds that were in the training data set and those that were not. And so that's a very exciting direction, and it works with the same kind of data. So the experiments that you're using are the same, you're just tweaking the machine learning side a little bit. But that's a very cool and exciting direction. So Bing actually followed up on the GC column question to use that to emulate a faster long sniff. So the question is largely around, could you use the GC column to emulate that fast long sniffing process? And you could certainly use a GC column to introduce a delay into the process. And it's something that I thought about using some kind of material to slow the process of the transport and limit it to just diffusion. The reason I thought about that a lot was when we inject the liquid into the chamber, we're introducing some convective processes, which we tried quantifying, but it's difficult to extrapolate how that looks for all compounds. So what you get is you drop something on the surface, and similar to a ball bouncing, some of the vapor will be ejected from the surface and move much faster than diffusion. And the idea was to use something like cotton or, as you suggested, a GC column to kind of prevent that convective transport in the column. And you could use the same thing in a gas-based sensor to remove things like turbulent flows and eddies that you get by injecting a liquid at high pressures or a vapor at high pressures. The reason we didn't do that is because there's a lot of complexity and in those processes that we don't fully understand. So if you're talking about liquid and vapor transport, laminar flows are very straightforward to understand, but turbulent flows are really complicated and we don't really know what's going on, right? And that's precisely the kind of dynamics that gives us the richness to mimic thousands of olfactory receptors with just a single sensor, right? So by keeping those complex processes, there's potential that the sensor will pick up on it and machine learning can learn from that information. So if the noise in your signal is potentially meaningful, machine learning can benefit from it. Versus if you filter all of that stuff out, then machine learning becomes less useful and you're less able to learn new physics and processes that are going on. It could be potentially very interesting for identifying different compounds. And so that was part of the motivation why we didn't introduce a GC or some kind of a blocker in the middle to limit it to processes that we did understand, and instead decided to leave all the stuff that we don't understand in it in the hopes that a robot could, right? Okay, Kelly asks, is it possible to incorporate this colorimetric sensor to low concentration bacteria and viruses rather than chemicals? That's a very interesting question that I thought about in the context of, could we use the sensor to detect things like mold, for example? And so mold spores are typically larger than bacteria, but the problem is probably going to be the same. So the sensor that we used in inverse opals, the kinds of sensors that we're talking about have pores on the order of a few hundred nanometers, with the connections between those pores being only tens, less than 100 nanometers in size. And the sensor that we used for the sniffing and smell-like sensors are much smaller, on the order of 10 to maybe 25 nanometer pores, with the interconnectedness being much smaller. And so when you're thinking about viruses, you're thinking about things that are tens of nanometers in size, depending on what you're talking about, and bacteria are much larger than that. And so the challenges there are, can you measure the object that you're actually interested in? In the context of spores, and in the context of molds, a lot of these molds will release chemicals that you can smell and give houses that very particular odor smell. So it's not always the spores that you're actually smelling; it's the chemicals that the mold is releasing. And so those chemicals you can again measure because they're much smaller than those nanometer-sized pores. But when you actually have to measure a particular virus or a bacteria, it might be much more effective and cheaper to use things like polymerase chain reactions that are very specific to a very specific virus. They're not necessarily as fast, but size is working a little bit against you in some of those occasions. So I don't see any more questions, but I'd be happy to stick around a little longer and see if anyone has any more follow-up questions But I also know that I'm not the final speaker, so I don't want to take everybody's time.
Okay. Thanks again for taking the time to give this presentation and answer all of our questions. Right now, there's actually a networking session, so if anyone wants to stick around for more questions, that's fine as well. And I should also let you know that in the Expo tab on the left there will be students sharing their research and I think recruitment sessions as well. So feel free to check those out.
Yeah, absolutely. It was a pleasure to be here. Thanks so much for inviting me. And, yeah.
Yeah. Yeah, and there are also other speakers if you want to check those out. The schedule's in the reception page, I believe.
Yeah, I didn't see those. And yeah, so I'll be checking around a little bit and see if I can make myself available at those network sessions.
All right, sounds good. Thanks so much.
Yeah, thank you so much, Mia.
Okay, see you.
Bye bye.